We're going to continue on with Chapter 2 today. The other day we talked a little bit about atomic theory, the discovery of the atom, the subatomic particles, how they learned that subatomic particles existed as well as where they're located. We talked about Dalton's atomic theory as well as the plum pudding model and Rutherford's gold foil experiment that established that there was a dense nuclear core where protons are located. What we're going to focus on today is first calculating the amount of subatomic particles, so how to figure out protons, electrons, and neutrons. Similar to our do now, I just want to review a few concepts. I know you've covered this in middle school, and we also really want to make sure you're clear on ions and isotopes, and you've worked through those POGIL packets, so hopefully you feel comfortable with both of those types of species. And then finally, in the second part of the lesson, we're going to be calculating weighted average atomic mass, and that will be a very new concept to you. It's not difficult, it's very mathy, and I feel very confident that you'll be successful with it. Your quiz on Monday will cover everything in Chapter 2, but the focus is more on the calculation of subatomic particles in atoms, ions, and isotopes, and also there'll be a question on weighted average atomic mass. And I think before you leave today, you'll feel very comfortable with all of these concepts. In your notes, where we left off last time would be right here. We want to talk a little bit about atomic number and mass number and how they relate to subatomic particles. In 1915, Henry Moseley talked about the concept known as atomic number. Now, when elements were first discovered, they really weren't talking much about atomic number. They were talking more about atomic mass. And you'll see the way the periodic table was originally constructed back in the 1860s in a subsequent chapter. Atomic number is abbreviated with a capital Z. And the atomic number is always, 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 always equal to which subatomic particle? Protons is correct. Maya, right? Alrighty. So always equal to the number of protons. Now all atoms are electrically neutral. They have no charge. So if you have an atom, is that big enough in the back? You wanted a little bigger? Oopsie, that wasn't very good. Like that. Maybe that's a little better. Yes, in the back you can see? Okay, great. So all atoms are electrically neutral, and so therefore the number of protons and electrons have to be equal. So you have an equal number of plus charge to negative charge for electric neutrality. Atomic numbers are always whole numbers. And let's take a look at the periodic table that I gave you last time. Since this is the one that you'll be using on all assessments, this is the periodic table I gave you last time. And for example, if we look in this first column, hydrogen has an atomic number of 1. It's a whole number, 1 proton for hydrogen. Lithium has an atomic number of 3, 3 protons for lithium. Sodium has an atomic number of 11, 11 protons for sodium. So if you know the atomic number, you know what element you're talking about because the atomic number is unique for each element. So essentially, it's an identification tag. If you look at the periodic table, and if we focus on this 4th row here, you'll see that elements are listed from left to right on the periodic table according to increasing atomic number. And we'll talk more about the organization of the periodic table 2 chapters from now. Now the mass number, abbreviated with a capital A as opposed to the Z for atomic number, is the total number of particles in the nucleus. And last time we said that protons and neutrons are located in the nucleus of the atom, and they account for 99.9% of the atom's mass. Electrons are outside the nucleus. Electrons are the lightest of the subatomic particles and don't really account for much mass. When we want to calculate the mass number, we simply add protons and neutrons together. Now be careful with the terminology here. The mass number is the rounded atomic mass. The atomic mass is what is reported on the periodic table. The atomic mass for the element sodium is 22.990 AMU for atomic mass units. So what's reported is the atomic mass. The mass number is the rounded atomic mass. So the mass number of sodium would be 23. The mass number of magnesium would be 24. So the mass number is the rounded atomic mass. And in the little do now that we worked on at the beginning of the period, I gave you the atomic mass. The mass number for rubidium is what? 85. And that's why we went over rounding earlier in the year, because you have to know how to round. So 85, and that's why the neutrons were just 85 minus 37 for 48. Okay? So on the periodic table is the atomic mass. The rounded atomic mass is the mass number. The whole number is the atomic number. There's some information here about the atomic mass, more than you need to know at this point. A few things I'd like you to take home. Atoms are very, very small. The unit is the atomic mass unit, and the equality for 1 AMU is about 1.7 times 10 to the negative 27 kilograms. Now for somebody who weighs about 110 pounds, that's about 55 kilograms. Well, this is 10 to the negative 27 kilograms, so that is teeny, teeny, weeny, and that's why we use atomic mass units to represent the unit, because this quantity is so small. The atomic masses that are listed on the periodic table are actually weighted average atomic masses. Many different isotopes exist for each element. In fact, elements, well, pure substances, consist of many, many different isotopes, and as a result, when you average them all together, you get a number in a decimal point format. And we're going to talk about weighted average atomic masses in the second part of the lesson, and we'll talk about how to calculate them. The standard for the atomic mass scale is carbon 12. Now 1 AMU is 1.7 times 10 to the negative 27 kilograms. That is not a quantity you need to memorize. The atomic mass unit is 1/12 the mass of one carbon 12 atom. And you're not going to have to do anything in terms of conversions there either, but the standard is C12, and that you would want to know. So carbon 12 is the standard for the atomic mass scale. We talked about the mole briefly in the introductory chapter, and we said that 1 mole is 6.02 times 10 to the 23rd particles. And we will use this conversion in great detail later in the year. Not something you have to concern yourself with either. You'll also understand later in the year how the atomic mass will be very important to make comparisons with other substances. If you know the mass of two substances that you have, you can compare them through the mole. And we'll talk about that later in the year as well. So as I indicated, there's a lot of information here, but not much that you need to walk away with now. Atomic mass is what's reported on the periodic table. The mass number is the rounded atomic mass. Atoms have very, very small masses. The unit is AMU, and carbon-12 is the standard. Those are the take-homes at this point. What we want to make sure that we're very comfortable with is calculating protons, neutrons, electrons, and from the do now it does appear that you are. We'll do a little bit of review here because you need to be really crisp here, and a lot of your quiz deals with this, and I want to make sure that you feel very confident going in so that you can do well. So the mass number we said is protons plus neutrons because those are in the nucleus, and the nucleus accounts for 99.9% of the mass of the atom. Shown here is the chemical symbol for potassium. This is the mass number if we considered potassium. Here's the atomic number, 39.098, mass number of 39, and the nomenclature you'll often see is this as a superscript on the left side here of the element. The atomic number, which we also get off the periodic table, is 19. If we want to calculate neutrons, we're going to do mass number minus atomic number, A minus Z. So how many neutrons would potassium have? 20 is correct. 19 protons, 19 electrons, 20 neutrons. Let's take a look at this series of examples. Let's work it together, and you're going to have a whole bunch that you'll be able to do. I'm going to make a little table. You probably could just drop lines down from the way I wrote it out for you. We've got fluorine. It's kind of little. Is that big enough in the back? That's good. Calcium. Try a little bigger. And bromine. And we want to figure out protons, electrons, and these are the abbreviations I mentioned the other day. Alrighty, so for fluorine, how many protons? 9 is correct. Electrons? 9 also. These are going to be the same because you have a neutral atom, no charge. And neutrons would be? 10 is correct. Excellent. Calcium? 20 is correct. Always, always, always equal to the atomic number. Electrons, we said, is the same. And how do we get neutrons? Subtract. 40 minus 20 is 20. And then bromine has how many protons? Good. How many electrons? And neutrons. Alrighty. Piece of cake, yes? Okay, good, because that you've seen since middle school. You're confident with that. Okay, it says cerium has an atomic number of 58 and an atomic mass of 140.12 AMU. What's the mass number for cerium? 140 is correct, the rounded atomic mass. How many protons? 58 is correct. How many electrons? 58 is correct. And the neutrons. And for those of you who don't like to do mental math, what's 140 minus 60? 80, right? And 2 more would be 82. Piece of cake? Cool. Alrighty, we want to talk about isotopes and ions. Questions at this point? Okay, let's see. And Dora, if I said to you an element has 37 protons, what would its atomic number be?
37.
Right. And if I said that the atomic mass of an element is 132.90, are you Sean? Okay. If I said to you that the atomic mass is 132.90, what's the mass number? 133. Correct, 133. Alrighty, we've got this. Isotopes. What does the prefix iso mean? What's an isosceles triangle?
It has different side measurements.
They're all different?
2 are the same.
2 are the same. So what does an isotope mean? But let's see. Which set A or set B, would be isotopes? Set A. Isotopes are atoms of the same element that differ in their mass number. Why are these not isotopes? Because they're not the same element. Those are actually called isobars, but we're not going to play there. Isotopes, atoms of the same element. So you have to have the same atomic number, you have to have the same element, and since the atomic number is unique, you would. They have different mass numbers. What differs, well, let me rephrase. Why would the mass number be different here? What subatomic particle differs for an isotope? Neutrons is correct. This one has 6 and this one has how many? 8 is correct. So what differs there is the neutrons. So in your notes it says atoms of the same element that contain different numbers of neutrons. Watch the spelling of neutrons, resulting in different mass numbers. And I've given you some examples here. I want you to see the different nomenclature here, and the POGIL packet really explained this nicely. So hopefully between the two, the concept will be solidified. Lithium-7 and lithium-8. Sometimes you write that particular designation with the superscript representing the mass numbers. Sometimes the mass number is after the dash. That is not a charge. That represents the mass number of the element. these two substances are isotopes. Similarly, H1 and H2. H2 is deuterium. You can use that in the lab to label things, although usually we use tritium. I didn't play with tritium that much. So H1 and H2 are isotopes. They differ in their number of neutrons, resulting in a different mass number. Most elements exist as a mixture of two or more isotopes. The reason that the mass is not expressed as a whole number on the periodic table, but rather as an atomic mass, is because of this variation in neutrons of the atoms. And we'll talk about that weighted average atomic mass in the second part of the lesson. The other thing I want to mention about isotopes before calculating protons, neutrons, and electrons is that some isotopes are radioactive, also referred to as radioisotopes. They have unstable nuclear configurations, and what will happen is the nuclei of these isotopes will disintegrate and the atom will emit radiation. And when you hear about nuclear warfare, etc., you're talking about radioactivity. If the atomic number is greater than 83, the isotope will be radioactive. Elements with atomic numbers greater than 83 have unstable nuclei. And we'll talk about why that is when we talk about nuclear chemistry later in the year. For example, radon has an atomic number of 86, so all isotopes of radon will be radioactive. If we were to look at a periodic table, it's not listed on the one I gave you simply because it's just too much. It just becomes too busy. But you'll see it on the back periodic table. You're not actually going to see it there. Let me pull one so you can see the symbol for radioactivity. So if you look at this periodic table here, you'll see here's element 83. Elements with an atomic number greater than 83 have isotopes that are radioactive. So polonium. Polonium is what they talked about in the movie Back to the Future, correct? You guys are a little young for that. It's a cute little movie. Astatine, radon is the one I mentioned. You'll see all of these radioactive isotopes here. So this is the symbol that means radioactivity. And when you walk into a laboratory, whether like it's at FAU or Scripps, if they use radioactivity in the lab, they'll have that symbol on the door because you'll need some type of protective guard so that you're not exposed to radiation. All right, let's take a look. We want to make sure we can do protons, electrons, and neutrons for each of the isotopes indicated. I'm going to make a table on this one too. I think it'll be easier to follow. So we have S32, the mass number for sulfur, and S35. We have I-125 and I-131. We have francium 223 and francium 229, and I indicated the atomic number for each of these in your notes. So how many protons would sulfur 32 have? Always equal to what? Atomic number. So these are both going to be 16. And there's no charge on an isotope, so protons and electrons have to be equal. You'd have 16 pluses, 16 minuses for net neutral. Now, how are we going to do neutrons for S32?
Subtract 16 from 32.
You got it. Subtract 16 from 32. And then this one we would do 35 minus 16, which is 19. Does that make sense? You're good? Okay. I-125. I-125, actually I'll back up a sec. S35 I've used in the laboratory. That's used to label proteins. And I-125 is very, very nasty. I've used that in the laboratory too. You can label up cells and also in Western blots. They don't use I-125 anymore. It's not very commonly used because it does cause problems with thyroid function. You need iodine for normal thyroid function. That's why you have iodized salt. But I-125 can negatively affect your thyroid, if you will. So what's protons for iodine? Protons is always equal to atomic number. And these are not charged particles, so that'll be the same. And how do we get this? 125 minus 53, correct? And this has 6 more, so 78. And let's see. Tori, how do we get protons for francium-223?
It's 87.
That is correct. And the electrons would be the same because
They're neutral.
it's neutral. And for neutrons, Victor,
146.
and how'd you get that?
I took away 87 out of 2, 2, 3.
And what'd you get?
I got 146.
136? And this has 6 more. Alrighty? Piece of cake. In the next set of problems, maybe I wrote your quiz like this. I just wanted you to be exposed to everything so that the quiz is easy for you. I think I mistakenly left the answers in there. I'm sorry, but we'll talk about how to get it. It says neon has 10 protons and 10 neutrons. What's the atomic number of neon? Why is it 10?
Atomic number is the amount of protons.
You got it. Atomic number is always equal to the number of protons. The mass number is 20. How do we get 20?
We have protons and neutrons.
You add protons and neutrons. Very good. The mass number for lithium is 7, and the atomic mass is 6.941. How did we determine that the mass number is 7? What did we do, Casey? You're not Casey. Sean. You look like Casey, though. You just rounded the atomic mass. Good. If lithium-10 exists, is it an isotope or an ion of lithium-7? Jenna, what do you got?
What was the question?
It's right here. It says if lithium-10 exists, is it an isotope or ion of lithium-7? Why is it an isotope? Because the number after the dash is? What does the number after the dash represent? Starts with an M. Mass number. There you go. Alrighty? Okay, the last thing we want to talk about in this section are ions. And ions are charged particles. Charged particles are formed through the loss or gain of one or more electrons. For those of you who want to work on your vocabulary, crossword puzzles are really good for that, and this is typically a clue in a crossword puzzle. It'll say charged particle, ion. Ions are either positive or negative. Cations are positively charged ions. And they have lost one or more electrons. They will have a positive charge, and positive means the loss of one or more electrons. The number before the charge indicates how many electrons have been lost. And I'll show you how to do that in this section here. It says determine the number of protons and electrons in the following. So let's take a look. We've got sodium, and we've got sodium ion. We've got calcium, and we've got calcium ion. And we have aluminum and aluminum ion. And we want to get protons and electrons. Oh, I'm sorry. I really do want eyes on the back of my head, then I could see better in both directions. Alrighty. How many protons does sodium have? $11. And the ion also, correct? Because protons never, ever, ever changes. Now the neutral atom has to have the same number of electrons, because if you have 11 positives and 11 minuses, you'd have net neutral, correct? Let me illustrate that differently. How about I do this? So if you have 11 pluses and 11 minuses, you're net neutral, no charge. Sodium ion has lost. As I said, that's just too big. See everything. The sodium ion has lost. A positive charge means the loss of one or more electrons, and there's an L right here. You can see it. So a plus charge means you have lost one electron. So now you have 10. So in the ion, if I've lost one electron, I have 11 pluses and 10 minuses for a net of 1 plus, hence the positive charge. calcium and calcium ion both have 20 protons. Never changes. The neutral atom has 20 electrons. Does the plus mean a loss or gain of electrons? Loss. The 2 means how many? So now you have 18. So you have 18 pluses, you have 20 pluses, 20 pluses, and 18 minuses for a net of 2 plus. You have 20 pluses and 18 minuses for a net of 2 plus. What about aluminum? How many protons? 13 for both, because that's not going to change. The atom will have 13 electrons, but the ion has how many electrons? 10 is correct, because it has lost 3. A positive charge. These circled in orange are cations, positively charged ions. And some of the kids will remember this by saying, oh, cats have paws, positively charged. Questions on cations. So if you gain electrons, then you are negatively charged, and these will be anions. So anions are negatively charged ions, and they have gained 1 or more electrons. So the negative means a gain of 1 or more electrons, and the number before tells you how many electrons have been gained. So let's look at a series of atoms and their corresponding anions. For example, we have chlorine and chloride ion. We have sulfur and a sulfide ion. We have nitrogen and a nitride ion, and we want protons and electrons. Now if I did protons initially, it'd be very easy because this is always, 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 always equal to the atomic number. Why are electrons for atoms the same as the proton?
To balance out the electric charge.
Exactly, to have a balanced charge, a net charge of 0. The negative sign indicates that the atom has gained an electron, in this case 1. Now you have an ion, an anion, and you'll have a gain of 1, so you have 18 electrons. For the sulfide ion, you have gain 2, so how many electrons would you have? 18. And this means, I wrote this incorrectly. This should be 3 minus here. I was sloppy. It's written correctly in your notes. This is a nitride ion, so it has gained how many? 3. And now has? And let's look at the charge in this one. You have 7 protons. The ion has 10 electrons. So the 7 pluses and the 7 minuses cancel, and here's the 3 minus charge that this ion has. So anions are negatively charged particles due to the gain of one or more electrons. Cations are positively charged ions due to the loss of one or more electrons. And keep this straight now, because you want to be comfortable with the fact that ions are formed due to the loss or gain of electrons, and isotopes are atoms of the same element due to a difference in neutrons. So keep that in mind. And by the time you finish the classwork, and especially those POGO packets which were assigned early, you'll be comfortable with that concept. Questions here? Okay, in your classwork, I'll give you about 20 minutes or so. You may not even need that much. I'm going to put your classwork on the screen here. You already have your classwork. This is the 1.3, the packet I gave you. You already completed parts 1 and 2. What I'm asking you to work on today in the next 20 minutes is part 3. I'd like you to work on this table as well as answer these questions. Don't do part 4 yet. After about 20 minutes, maybe 15, because I don't think it'll take you very long, we're going to talk about weighted average atomic mass. It's just problem solving. It's very, very easy, and you'll be highly successful with it. So I'll give you some time now to work on your classwork. If you have any questions, please don't hesitate to ask. Hopefully you have a very high comfort level with finding subatomic particles in atoms, ions, and isotopes.